Tonight, we are going to explore the biggest star humanity has ever identified. A star so vast that if it were somehow placed where our Sun is, its luminous outer layers would extend far beyond the orbit of Saturn. The inner worlds, Mercury, Venus, Earth, Mars, and even the massive Jupiter, would all be completely engulfed, lying deep within the outer atmosphere of this colossal star. By the time we finish tonight, you will understand how scientists uncovered a star that is barely able to remain intact against the pressure of its own radiation, why it exists right at the boundary of what the laws of nature permit, and how its discovery forced us to rethink everything we believed about the ultimate limits of how large a star can truly become. Now, let's begin. The year was 1990. Astronomer Charles Bruce Stephenson was carrying out a detailed and systematic survey of the sky, searching for massive star clusters concealed within the dusty regions of our galaxy. His attention was focused on the constellation Scutum, a relatively small and dim grouping of stars in the southern sky that lies directly along the plane of the Milky Way. This area is densely packed with stars, gas, and dust. It is one of those regions where the Milky Way looks especially bright and crowded, yet at the same time heavily obscured. The abundance of dust makes it extremely difficult to clearly observe what is actually present there. By using infrared observations, which can pass through dust far more effectively than visible light, Stephenson detected a cluster of stars located approximately 19,000 light-years from Earth. This was no ordinary cluster. It contained some of the most massive and most luminous stars he had ever encountered. Red supergiants, blue supergiants, stars releasing hundreds of thousands of times more energy than our Sunday. This cluster was later named Stephenson 2. And for many years it remained an intriguing but relatively overlooked object within astronomical catalogues. It was considered just another massive young cluster among the many thousands found in our galaxy. However, as infrared astronomy progressed throughout the 1990s and 2000s, and as new space telescopes such as Spitzer and Herschel became operational, astronomers began to examine Stephenson 2 with much greater precision. Gradually, they noticed something extraordinary. One particular star stood out clearly from the rest. It appeared exceptionally bright in the infrared spectrum, far brighter than what would normally be expected from a typical red supergiant. Its brightness was so extreme that it suggested either the star was significantly closer than the rest of the cluster, which seemed unlikely, or that it was extraordinarily large. This star was labeled Stephenson 218, the 18th star catalogued within the cluster. At that time, no one realized that they might be observing the largest star ever discovered. That understanding came later, as astronomers began the careful and demanding process of measuring the star's physical characteristics. And this is where the real challenge begins. How do you measure a star that lies 19,000 light-years away? You cannot send a spacecraft there. You cannot obtain a detailed close-up image. Instead, you must rely entirely on photons of light that have traveled across space for 19,000 years. Light that departed from this star at a time when humans were still living in small hunter-gatherer communities, long before the construction of the pyramids, long before the development of writing, agriculture, or civilization. Those ancient photons finally reach our telescopes, and from them we must reconstruct everything about this distant star. Its temperature, its brightness, its size, its mass, its composition, all of it must be inferred from light alone. The first step is determining brightness. This part is relatively simple. You aim a telescope at the star, collect its light, and measure how much energy is received. This gives what astronomers call apparent magnitude, which describes how bright the star appears from Earth. In the case of Stephenson 218, its apparent magnitude is actually quite faint. It cannot be seen with the naked eye. Even through a small telescope, it can easily be lost among the thousands of other stars in that crowded region. However, infrared observations reveal that it is in fact quite bright in the infrared, much brighter than it appears in visible light. This is expected for a cool star, since cooler stars emit most of their energy in the infrared part of the spectrum rather than in visible wavelengths. The next requirement is distance. Brightness alone is not enough, because a faint nearby star and a bright distant star can appear equally bright when observed from Earth. To determine the star's true intrinsic brightness, known as luminosity, you must know how far away it is. For stars within a few thousand light years, astronomers can use parallax. As Earth moves around the Sun, nearby stars seem to shift slightly against the background of more distant stars. By measuring this tiny shift, distances can be calculated using simple geometry. But parallax is only effective for relatively nearby stars. At a distance of 19,000 light-years, the shift becomes far too small to measure, even with advanced space telescopes. Because of this, astronomers must rely on alternative techniques. Since Stephenson 218 belongs to a cluster, they can estimate its distance by analyzing the cluster as a whole. By studying the properties of many stars within the cluster and comparing them with theoretical models, they can constrain the cluster's distance. Different methods produce slightly different results, which is why estimates for Stephenson 2 range between about 17,000 and 20,000 light-years. For practical purposes, 19,000 is taken as the best estimate, with both brightness and distance known. Astronomers can then calculate luminosity, the total amount of energy the star emits each second. The result was astonishing. Stephenson 218 has a luminosity approximately 440,000 times greater than that of our Sunday. Every single second, this star releases 440,000 times more energy than our Sun produces. That represents an almost unimaginable level of power. But brightness by itself doesn't directly reveal a star's size. A compact, extremely hot star can shine intensely, while a much larger but cooler star can also appear highly luminous. To determine size, temperature is essential. This is where spectroscopy becomes crucial. By breaking the star's light into a spectrum and examining which wavelengths appear, astronomers can estimate the temperature at the star's surface. Different temperatures create distinct spectral patterns. Hot stars display different absorption lines compared to cooler ones. The spectrum of Stephenson 218 made something clear right away. This is a cool star, exceptionally cool. Its surface temperature is only around 3,600 Kelvin, which corresponds to roughly 6,000 degrees Fahrenheit. That may sound extremely hot by everyday standards, and it is, but in stellar terms it is relatively cool. Our Sun's surface temperature is about 5,770 Kelvin, more than 10,000 degrees Fahrenheit. So, Stephenson 218 is cooler than the Sunday. That is why it appears red. Cooler stars glow red, while hotter ones shine blue or white. The spectrum also revealed molecules within the star's atmosphere. Titanium oxide, water vapor, carbon monoxide. These molecules can only survive at comparatively low temperatures. In hotter stars, they would be torn apart. Their detection confirmed it. This is a cool hypergiant. Now comes the key calculation. If you know the total energy a star emits, its luminosity, and you also know its surface temperature, you can determine how large it must be. This relies on a relationship known as the Stefan-Boltzmann law. According to this law, the total energy output of a star depends on two factors: the temperature of its surface, because hotter surfaces emit more energy per unit area, and the total surface area itself. A cool star that is extremely luminous must have a vast surface area to radiate that much energy. When astronomers applied the numbers for Stephenson 218, the outcome was astonishing. The radius of the star was calculated to be roughly 2,000 to 2,400 times the radius of our Sunday. To put that into perspective, the Sun's radius is about 433,000 miles. Multiply that by 2,000, and you get a radius of roughly 930 million miles. That is the distance from the center of the star to its surface. The diameter, the full distance across, is about 1,860,000,000 miles. Stephenson 218 is the largest star ever identified in the known universe. And now that you understand how astronomers detected it and measured it, let's examine what that actually implies. A radius of 930 million miles is such a massive number that it's difficult to grasp without comparison. So let's try to picture it. If you could somehow replace our Sun with Stephenson 218 while leaving the rest of the solar system unchanged, here's what would occur. The center of the star would remain where the Sun's center is today, but instead of the Sun's surface being 433,000 miles away, Stephenson 218's surface would stretch out to about 10 astronomical units from the center. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. So, this star's surface would lie at 10 times that distance. Mercury orbits at about 0.4 astronomical units. It would be far inside the star, completely swallowed. Venus, at 0.7 astronomical units, would also be inside. Earth, at 1 astronomical unit. The very distance we use as a standard would not even come close to the surface. It would sit deep within the star's outer layers. Mars, at 1.5 astronomical units, would be inside as well. The asteroid belt between 2 and 3 astronomical units would be entirely enclosed within the star. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Even Jupiter would find itself immersed in the star's glowing atmosphere. Saturn, with its rings, orbits at roughly 9.5 astronomical units. Stephenson 218's surface would extend beyond Saturn's orbit. If you were somehow standing on Saturn and looked upward, you wouldn't see a small bright dot in the sky. Instead, you would see an enormous, dim red surface filling the entire sky, glowing like burning embers. You would already be inside the star. Only Uranus, at 19 astronomical units, and Neptune, at 30 astronomical units, would remain outside the star's surface. The Kuiper belt, that distant region of icy bodies beyond Neptune, would stay far out in the darkness, beyond the reach of this cosmic giant. Now let's consider volume. The volume of a sphere increases with the cube of its radius. If Stephenson 218 has a radius about 2,000 times greater than the Sun's, then its volume is 2,000 cubed. That is 2,000 multiplied by 2,000 multiplied by 2,000, around 10 billion. You could fit approximately 10 billion suns inside Stephenson 218, not 10, not 100, not even a million, 10 billion. If our Sun were the size of a tennis ball, Stephenson 218 would be a sphere about 1,000 feet across, roughly as tall as a 100-story skyscraper. If our Sun were a marble, Stephenson 218 would be larger than an ordinary house. The sheer scale involved is truly hard for the human mind to grasp. But this is where things become even more unusual. Even though it is about 10 billion times greater in volume, Stephenson 218 contains only around 12 to 16 times the mass of our Sunday. How can that be? The key lies in density. Stephenson 218 belongs to a massive stellar cluster known as Stephenson 2, which was identified in 1990 by astronomer Charles Bruce Stephenson. This cluster lies along the galactic plane, surrounded by thick clouds of dust and gas. Because of this, observing it is extremely challenging, as the dust both absorbs and scatters light, especially in the visible spectrum. Early studies of the cluster relied on infrared telescopes, since infrared light can pass through dust more effectively than visible light. These observations revealed that Stephenson 2 hosts some of the most massive and brightest stars ever known. Among them, one object stood out clearly. Stephenson 218 displayed properties indicating it was extraordinarily large, even when compared with other hypergiants in the same cluster. Determining the size of a star at such a distance requires indirect approaches. You cannot simply aim a telescope at it and measure its diameter the way you would measure the moon. At a distance of 19,000 light-years, even the largest stars appear only as tiny points of light. Instead, astronomers rely on multiple methods working together. First, they determine the star's brightness, or apparent magnitude, which tells us how bright it looks from Earth. Then they estimate its distance through different techniques, often by analyzing the cluster to which it belongs. With brightness and distance, they can calculate luminosity, the total energy the star emits each second. Stephenson 218 has a luminosity about 440,000 times greater than that of our Sunday. In other words, every second it releases 440,000 times more energy than our Sun produces. After that, astronomers determine the star's temperature by studying its spectrum, observing how its light spreads into different colors. Different temperatures create distinct spectral patterns. Stephenson 218 has a surface temperature of about 3,600 Kelvin, which is roughly 6,000 degrees Fahrenheit. That may sound extremely hot, and it is, but for a star, it is actually relatively cool. The Sun's surface temperature is around 5,770 Kelvin, or about 10,000 degrees Fahrenheit. This means Stephenson 218 is cooler than the Sun, which is why it shines with a red color instead of a yellow-white glow. Cooler stars appear red, while hotter ones appear blue or white. Once luminosity and temperature are known, astronomers can calculate the star's radius using a relationship called the Stefan-Boltzmann law. This law connects luminosity with temperature and surface area. A star that is relatively cool, yet extremely luminous, must have a vast surface area to emit such an enormous amount of energy. Calculations for Stephenson 218 suggest a radius between 2,000 and 2,000, 400 times that of the Sunday. There is some uncertainty because measuring exact temperature and luminosity at such distances introduces unavoidable margins of error. Even so, at the lower end of these estimates, the star is almost beyond comprehension in size. A radius of 2,000 times that of the Sun corresponds to about 930 million miles, or roughly 1,860,000,000 miles across in diameter. At the upper estimate of 2,400 solar radii, the radius reaches approximately 1,120,000,000 miles, giving a diameter of about 2,240,000,000 miles. Either way, it stands as the largest star ever discovered. There are other candidates that have been proposed. Stars such as UY Scuti, VV-Cafe and WOG-64 have each at different times been considered contenders for the title of the largest known star. As observational tools improve and data becomes more precise, these measurements continue to be refined. For a period, UY Scuti held the record with an estimated radius of around 1,700 solar radii. But newer, more accurate measurements have revised that figure down to about 755 solar radii, making it significantly smaller than once believed. Stephenson 218, based on current data, appears to be larger, although astronomy is always evolving as new observations are made. Future instruments with greater precision may adjust these numbers further. What can be said with confidence is that Stephenson 218 ranks among the largest stars ever identified, and it is very likely the largest known so far. Now consider this question: why does a limit exist on how large a star can grow? It might seem that with enough mass, a star could continue increasing in size indefinitely, but stellar physics does not allow that. There are strict limits set by the fundamental forces of nature. Stars shine because of nuclear fusion occurring in their cores. Hydrogen atoms fuse into helium, releasing energy in the process. This energy produces an outward pressure that pushes against the inward pull of gravity. A star exists as an ongoing struggle between two opposing forces. Gravity works to pull everything inward, compressing the star, while the pressure generated by nuclear fusion pushes outward, trying to expand it. When these two forces reach equilibrium, the star remains stable. However, extremely massive stars, those exceeding roughly 8 to 10 times the mass of the Sun, live intense but short lives. They consume their fuel at extraordinary rates. The greater the mass of a star, the hotter and denser its core must become in order to generate enough pressure to counteract gravity. This elevated core temperature causes fusion reactions to proceed much more rapidly. As a result, massive stars exhaust their hydrogen supply in only millions of years rather than billions. Once the hydrogen in the core is depleted, the star begins fusing helium into carbon. When helium is used up, carbon fusion begins, producing heavier elements. This sequence continues upward through the periodic table, forming oxygen, neon, magnesium, silicon, and eventually iron. Each successive stage yields less energy than the previous one and occurs over a shorter timescale. A massive star may spend millions of years fusing hydrogen, thousands of years fusing helium, hundreds of years burning carbon, and only a matter of days fusing silicon into iron. Iron marks the end of this process. Fusion involving iron does not release energy. Instead, it requires energy input. Once an iron core forms inside a massive star, fusion effectively stops. The outward pressure disappears and gravity takes over. The core collapses in a fraction of a second, leading to a supernova explosion. Now, this is crucial for understanding the limits of stellar size. As a star evolves beyond the main sequence and begins fusing heavier elements, it expands. While the core contracts and becomes hotter, the outer layers stretch outward and cool. This is why aging massive stars transform into red supergiants or, in more extreme cases, hypergiants. Stephenson 218 is classified as a hypergiant. It is in an advanced stage of stellar evolution, nearing the end of its lifespan. Its immense size is the result of a contracting core combined with an expanding outer envelope. However, there is a boundary to how far this expansion can go. That boundary is defined by what is known as the Eddington limit. This limit represents the point at which the outward force of radiation becomes strong enough to overcome gravity and begins to push the star apart. Stars emit light, and light carries momentum. As photons stream outward from a star, they exert pressure on the atoms in the outer layers. In ordinary stars, this radiation pressure is negligible compared to gravity, but in extremely luminous stars, it becomes significant. In hypergiants such as Stephenson 218, radiation pressure is enormous. This star emits 440,000 times more light than our Sunday. All of those outward-moving photons are constantly pushing against the star's outer layers. If the luminosity increased even slightly for its mass, radiation pressure would surpass gravity, and the outer layers would be expelled into space. This is exactly what occurs in the most massive stars. They lose mass through powerful stellar winds, continuously shedding material. Stephenson 218 is almost certainly undergoing this process. Its outer envelope is likely being slowly stripped away by its own radiation. Over time, the star will lose so much mass that it can no longer sustain its enormous size. It will eventually collapse, trigger a supernova, and most likely leave behind either a neutron star or a black hole. Therefore, the upper limit of a star's size is not simply about how much mass it contains. It is determined by the balance between gravity, radiation pressure, and the star's stage of evolution. Stephenson 218 exists near that limit. If it were any larger, it would likely tear itself apart. Now imagine what it might be like to approach this star. Picture yourself aboard a spacecraft traveling toward Stephenson 218. From several astronomical units away, the star would dominate your entire field of view. It would no longer appear as a distant point of light, but as a vast, glowing surface stretching across the sky. As you moved closer, its reddish hue would become increasingly noticeable. This is a relatively cool star by stellar standards, shining in red-orange tones rather than white or blue. Its surface would appear dim compared to the Sunday. Despite being 440,000 times more luminous overall, its light is spread across such an enormous area that its surface brightness is actually quite low. If it were somehow possible to stand on a platform at the star's surface and look around, the surroundings would not appear blindingly bright. Instead, the glow would be subdued, resembling the soft radiance of hot embers in a fire. It might even be possible to look directly at the surface without instantly destroying your eyes, although the intense infrared radiation would still prove fatal very quickly. The primary danger would not be visible light, but heat. Even though the surface temperature is only about 3,600 Kelvin, the sheer volume of radiation being emitted would incinerate anything nearby. At a distance equivalent to Earth's orbit from the center of this star, assuming survival within its outer envelope were somehow possible, temperatures would still reach several thousand degrees. Under such conditions, all matter would exist as plasma. No solid material could survive. As you moved closer toward the center, the temperature would rise dramatically, reaching into the millions of degrees. At the heart of Stephenson 218, where nuclear fusion actively occurs, the temperature is believed to climb to several hundred million degrees Kelvin. Under such extreme conditions, matter can no longer exist in its usual form, breaking apart into bare atomic nuclei and freely moving electrons. The pressure in this region is millions of times greater than the atmospheric pressure on Earth. No structure resembling anything solid or stable could survive there. It is a domain governed entirely by energy and the most fundamental particles. One of the most extraordinary aspects of Stephenson 218 is how brief its existence truly is. Stars of this kind are not only rare in space, but also fleeting in time. Our Sun, for comparison, has an estimated total lifespan of around 10 billion years. It is currently about 4.6 billion years old, placing it roughly halfway through its life cycle. It will continue converting hydrogen into heavier elements for another 5 billion years before exhausting its fuel and expanding into a red giant. Stephenson 218, on the other hand, is expected to live only about 20 million years in total, possibly even less. It may have already undergone a supernova explosion, and we would not yet be aware of it because the light from that event is still traveling through space toward us. Keep in mind, this star lies 19,000 light-years away. What we observe today is actually the state of the star as it was 19,000 years ago. If it exploded 10,000 years ago, we would still have to wait another 9,000 years before that light reaches Earth. This imbalance in time is one of the strange consequences of observing objects across such vast distances. In essence, every time we look out into space, we are looking into the past. When Stephenson 218 eventually reaches the end of its life, and it inevitably will, the resulting explosion will be extraordinary. Hypergiants, like this, are believed to conclude their evolution in supernova events, and possibly even hypernovae, which are far more powerful than standard supernovae. A hypernova can release an immense amount of energy, potentially enough to generate a gamma-ray burst. Gamma-ray bursts are among the most energetic phenomena in the universe, surpassed only by the Big Bang itself. In just a few seconds, they can emit more energy than our Sun will produce over its entire 10 billion-year lifetime. If Stephenson 218 produces such a burst at the moment of its death, and if that burst happens to be directed toward Earth, it could be visible to us despite the immense distance of 19,000 light-years. It would appear as an intensely bright point of light within the constellation Scutum, possibly even visible during daylight for a brief time. However, there is no cause for concern. At such a distance, the radiation would be scattered and absorbed by interstellar matter long before reaching our planet. We would remain completely safe, witnessing only an extraordinary cosmic display. Following the explosion, the remnants of the supernova would expand outward at a considerable fraction of the speed of light, colliding with surrounding gas and forming a glowing nebula. This nebula would remain visible for thousands of years, gradually fading as it cools and disperses into space. Meanwhile, the core of the star would collapse. Based on current estimates, with a mass somewhere between 12 and 16 times that of the Sun, Stephenson 218 sits right at the threshold between forming a neutron star or collapsing further into a black hole. Neutron stars are typically formed from stellar cores with masses between about 1.4 and 3 solar masses. Beyond that range, gravitational collapse continues until a black hole is formed. The final outcome for Stephenson 218 depends on how much mass it has lost over time through powerful stellar winds. If it has shed enough material, the remaining core could stabilize as a neutron star. If not, it may collapse completely into a black hole. In either case, the hypergiant itself will cease to exist, leaving behind only a dense and compact remnant. To better understand how extreme Stephenson 218 is, it helps to compare it with other types of stars. Our Sun is classified as a G-type main-sequence star, considered fairly average in both size and mass. In fact, most stars in the galaxy are smaller and cooler than the Sunday red dwarfs, which are the smallest stars capable of sustaining nuclear fusion, account for roughly 70% of all stars. A typical red dwarf might have a radius only 20% that of the Sun, and a mass between 50% of the Sun's mass. But these stars are small, faint, and remarkably long-lived, with the smallest among them capable of burning for trillions of years. At the opposite end of the spectrum are blue supergiants and hypergiants, which are massive, extremely hot, and incredibly luminous. Rigel, the bright blue star located in Orion's foot, is an example of a blue supergiant, with a radius about 79 times that of the Sunday. While enormous compared to our Sun, it is still tiny when measured against Stephenson 218. Then there are red supergiants, cooler stars that have expanded to tremendous sizes. Betelgeuse, the well-known red star in Orion's shoulder, is perhaps the most famous example. Its size fluctuates due to pulsations, but estimates suggest a radius of around 764 times that of the Sunday. That alone is immense. If Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Mars, possibly reaching into the asteroid belt. And yet, even with that staggering scale, Stephenson 218 remains nearly 3 times larger. Antares, a well-known red supergiant located in the constellation Scorpius, possesses a radius of roughly 680 solar radii. VVC Phi, counted among the largest red supergiants identified so far, reaches a radius close to 1,500 solar radii, yet it remains smaller than Stephenson 218. Ui Scuti, which for a period was believed to be the largest star, currently has an estimated radius of about 755 solar radii, although earlier calculations placed it significantly higher. The key point is that even when compared with other enormous stars, Stephenson 218 clearly stands apart. It occupies a category of its own. Now, there is an important detail that needs to be clarified. Determining the radii of stars, particularly distant red hypergiants, is extremely challenging. These stars are frequently surrounded by dense envelopes of dust that they themselves have expelled. This dust absorbs and diffuses light, making it difficult to define exactly where the surface of the star truly lies. Furthermore, many of these stars undergo pulsations, expanding and contracting over periods of months or even years. Their dimensions are not fixed. Stephenson 218 may appear larger at certain times and smaller at others. The measurements available to us represent only snapshots, and they include margins of uncertainty. The estimated radius of 2,000 to 2,400 solar radii is therefore a range, not an exact value. Future observations using more advanced instruments may refine these figures. It is possible that another star could eventually be identified as larger. It is also possible that improved measurements might reveal Stephenson 218 to be smaller than currently believed. However, Based on the most reliable data we have today, it remains the largest. Now, let's turn our attention to the cluster that this star belongs to. Stephenson 2 is classified as an open cluster, meaning it is a collection of stars that form together from the same molecular cloud. By stellar standards, the cluster is relatively young, with an age of only about 20 million years. It contains some of the most massive stars in the galaxy, including several red supergiants and hypergiants. Its position within the galactic plane places it inside regions of dense star formation. Nearby, new stars are actively being born. This environment is abundant in gas and dust, the essential ingredients for star formation. Stephenson 2 is considered one of the most massive young clusters in the Milky Way, with a total stellar mass estimated between 50,000 and 100,000 solar masses. Among its notable members are Stephenson 2, 3, another red hypergiant, and Stephenson 2, 7, which is also a red supergiant. These stars are all massive and are currently in the late phases of their evolution. Within a few million years, many of them are expected to end their lives as supernovae. Over time, the cluster itself will be disrupted by these explosive events as well as by gravitational interactions between its stars. Young clusters like Stephenson 2 do not remain intact for long. Over tens of millions of years, their stars gradually drift apart, dispersing into the wider galaxy. The cluster we observe today is therefore only a temporary grouping. It represents a brief moment in the history of the galaxy when many massive stars happen to share the same region of space. In about 100 million years, Stephenson 2 will no longer exist as a cluster. Its stars will have spread out across a much larger portion of the galaxy. However, the impact of these stars will persist. When they explode, they will enrich the interstellar medium with heavy elements. Carbon, oxygen, nitrogen, silicon, iron, and many other elements are forged within their cores, and during their supernova explosions, these materials will become part of new clouds of gas and dust. Those clouds will eventually collapse, forming new stars and planetary systems. The atoms that make up your body, the iron circulating in your blood, the calcium in your bones, and the oxygen you breathe all originated in stars. Much of it was produced in stars similar to Stephenson 218. Massive stars function as the universe's factories for elements. They are the places where chemical complexity is built. Without massive stars, the universe would consist almost entirely of hydrogen and helium. There would be no rocky planets, no liquid water, and no life. Stars like Stephenson 218 are uncommon, but they are essential to the universe's capacity to generate complexity. They burn brightly, live briefly, and in their final moments, they distribute the raw materials needed for future worlds. Now, let's consider a common question. Could life exist on a planet orbiting a star such as Stephenson 218? The simple answer is no, not in any form we would recognize. First, the lifespan of the star is far too short. Life on Earth required billions of years to develop. Simple single-celled organisms appeared around 3.8 billion years ago. Complex multicellular life did not emerge until approximately 600 million years ago. Intelligent life is even more recent. A star like Stephenson 218 has a total lifespan of only about 20 million years. That is nowhere near enough time for life to evolve from basic chemistry. Second, the environment around such a star is extremely hostile. Even if a planet somehow managed to form in orbit before the star became a hypergiant, which is unlikely, that planet would be exposed to intense radiation. The brightness of the star changes as it undergoes pulsations. Its powerful stellar winds would continuously strip away any atmosphere present. When the star expanded into a hypergiant phase, it would have swallowed any planets orbiting nearby. Worlds that originally lay within the habitable zone would have been completely vaporized as the star grew larger. Third, stars of such immense mass release significant amounts of ultraviolet radiation and X-rays. This intense, high-energy radiation would tear molecules apart, making it extremely difficult for complex chemistry to persist on any planet in close proximity. The only possible way for a planet to remain habitable around such a star would be to orbit at a very large distance, many astronomical units away, far beyond the star's expanded outer layers. Yet even in that scenario, the lifespan of the star would be too brief and the radiation conditions far too extreme. So no, planets orbiting hypergiants are not favorable environments for life. Life, based on our current understanding, requires stable conditions maintained over long periods of time. It needs a star that shines consistently for billions of years, delivering a steady supply of energy. It also requires liquid water, organic compounds, and sufficient shielding from harmful radiation. Hypergiants offer none of these conditions. They are extraordinary objects and play a vital role in the chemical evolution of the universe. But they are not places where life can emerge or survive. The most promising locations to search for life are around stars similar to the Sun. Medium-mass stars that burn steadily for billions of years, providing consistent energy over geological timescales. Alternatively, life might exist around red dwarfs, the smallest type of stars, which can burn for trillions of years, although they present their own difficulties, such as frequent flares and tidal locking. Hypergiants are remarkable, but they function as cosmic factories, not as cradles for life. They produce the elements necessary for life, yet they do not host it. Here is another perspective to consider. What if it were possible to harness the energy of a star like Stephenson 218? The concept known as a Dyson sphere, a massive structure designed to surround a star and capture its energy, was introduced by physicist Freeman Dyson in 1960. The idea suggests that an advanced civilization could construct a vast swarm of energy collectors orbiting a star, capturing a large portion of its total energy output. For a star like the Sun, this would already provide an immense amount of energy, far exceeding what humanity currently consumes. For a star such as Stephenson 218, the available energy would be almost unimaginable. Keep in mind that this star emits 440,000 times more energy than the Sun. Capturing even a small percentage of that output would provide power on a scale that is nearly beyond comprehension. However, constructing a Dyson sphere around Stephenson 218 would be highly impractical for several reasons. First, the star's lifespan is far too short. By the time such a megastructure could be completed, the star would already be approaching the end of its life. Enormous resources would be invested into a project that would last only a few million years, at most, before the star exploded, destroying everything around it. Second, the star is so enormous that the amount of material required to build a surrounding structure would be overwhelming. Constructing a solid shell around a star with a radius of 2 billion miles would demand more material than is available in the entire solar system. It would require dismantling thousands of planetary systems just to gather enough raw resources. Third, the star's extreme radiation and violent stellar winds would make both construction and maintenance extraordinarily difficult. Any structure would face constant exposure to high-energy particles and radiation. It would need to be incredibly durable, far beyond anything we can currently conceive of building. A more realistic approach would be to construct a Dyson sphere around a stable, long-lived star. A star like the Sun, or perhaps a red dwarf? Stars that shine steadily for billions of years, offering reliable energy for the entire lifespan of a civilization. Stephenson 218 is astonishing, but it is not a suitable candidate for long-term energy collection. It is too unstable, too short-lived, and far too violent. Now, let us step back and consider the role of stars like Stephenson 218 inches, the evolution of the galaxy. The Milky Way has been forming stars for more than 13 billion years. Over that immense span of time, countless generations of stars have been born, lived out their life cycles, and eventually died. The earliest stars, known as population 3 stars, formed from pure hydrogen and helium. At that time, heavy elements did not yet exist, because such elements are created inside stars. These first stars were likely extremely massive, burning intensely and rapidly, ending their lives as supernova explosions after only a few million years. Their explosive deaths spread the first heavy elements throughout the universe: carbon, oxygen, nitrogen, silicon, magnesium, iron. These elements combined with the remaining hydrogen and helium, forming chemically enriched clouds of gas. The next generation of stars, called population 2 stars, formed from this slightly enriched material. They contained small amounts of heavy elements, enough to allow more complex chemistry to take place in the surrounding environments. Our Sun belongs to population I stars, representing the most recent stellar generation. It came into existence roughly 4.6 billion years ago, forming from gas that had already been enriched by several earlier generations of stars. The planets in our solar system, including Earth, were created from material containing about 2% heavy elements by mass. That 2% originated entirely from stars that lived and died before our Sunday. Stars such as Stephenson 218 are part of this continuous cycle. When such a star eventually explodes, it disperses heavy elements into the interstellar medium. Over time, those elements become incorporated into new stars and planetary systems. This is the process through which the galaxy steadily becomes richer in metals. In astronomy, any element heavier than helium is referred to as a metal, even though most of them are not metals in the chemical sense. When scientists describe a star as metal-rich, they mean it contains a relatively higher proportion of elements heavier than helium. Metal-rich stars tend to be younger because they formed from gas that had been processed through multiple previous stellar generations. In contrast, metal-poor stars are older, having formed from less enriched material. Stephenson 218 is considered a young, metal-rich star. It formed from gas already containing substantial amounts of heavy elements created by earlier stars. When it reaches the end of its life, it will contribute even more heavy elements to its surroundings, further driving the chemical evolution of the galaxy. This entire process explains how the universe is able to build complex structures. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Every other element, every atom of carbon in your body, every atom of oxygen you breathe, and every atom of iron in Earth's core was forged in stars. A large portion of those elements originated in massive stars like Stephenson 218. These stars act as the universe's alchemists, transforming simple elements into more complex ones. Their lifespans are short, but their brilliance is immense. In their deaths, they enrich the cosmos. Without them, the universe would be far simpler and far less fascinating. Now consider observation. How do we actually examine a star like Stephenson 218? It is not as though we can send a spacecraft there. At a distance of 19,000 light-years, even traveling at the speed of light would require 19,000 years to arrive. No human-made probe is capable of such a journey. Voyager 1, the fastest and most distant spacecraft we have launched, has been traveling for more than 47 years and has covered only about 0.002 light-years. At that pace, it would take millions of years to reach Stephenson 218. As a result, we rely entirely on remote observation using telescopes. We gather the light emitted by the star, separate it into a spectrum, and analyze the resulting patterns. Each element absorbs and emits light at specific wavelengths. By identifying which wavelengths appear or are missing, we can determine the star's composition, temperature, motion, and other physical properties. We can also monitor how the star's brightness changes over time. Many red hypergiants are variable stars, meaning their brightness fluctuates periodically. These variations are caused by pulsations, as the star expands and contracts, altering its size and temperature, and therefore its brightness. By carefully tracking these changes, we gain insight into the star's internal structure and behavior. Some observations are made using visible light, but many rely on infrared wavelengths. Stephenson 218 is heavily obscured by dust, both within its cluster and in the interstellar space between it and us. Infrared light can penetrate dust more effectively than visible light, allowing astronomers to see through this obscuration. Radio observations are also valuable. Stars emit radio waves, and studying them can reveal details about stellar winds, magnetic fields, and other processes. Interferometry, which combines light from multiple telescopes to function as a single, larger instrument, can achieve much higher resolution. This method has been used to directly measure the sizes of some nearby giant stars. For objects as distant as Stephenson 218, interferometry is difficult, though it may become feasible with sufficiently large baselines. Most of our knowledge comes from photometry and spectroscopy. Photometry involves measuring brightness, while spectroscopy focuses on analyzing the spectrum. Together, these techniques provide a remarkably complete understanding of a star's characteristics. From light that has traveled 19,000 light-years, we can determine its temperature, luminosity, composition, mass, radius, age, and evolutionary stage. This stands as a powerful demonstration of human ingenuity and the predictive strength of physics, allowing us to learn so much about an object we will never physically visit. Here is something to consider. How many stars like Stephenson 218 exist in our galaxy? The answer is very few. Hypergiants are extremely rare. Among the hundreds of billions of stars in the Milky Way, only a few dozen hypergiants have been identified. This scarcity arises partly because hypergiants are truly rare, and partly because they are difficult to observe. Many are hidden behind thick clouds of dust, situated in far-off or densely populated regions, and they have relatively short lifespans. Even if our galaxy produces a hypergiant once every few thousand years, each of these stars survives only a few million years. As a result, at any specific moment, There may be only a few thousand of them spread across the entire galaxy, and most remain too distant or too obscured for us to detect. The examples we have identified tend to be relatively nearby, within a few tens of thousands of light years. Stephenson 218, located about 19,000 light-years away, is among the more distant ones that scientists have examined in detail. It is highly likely that additional hypergiants exist even farther away, concealed from our view by vast distances and intervening dust. As our instruments become more advanced and our surveys expand to cover more of the sky, we will likely uncover more of them. Still, hypergiants will always remain uncommon. They represent a brief and extreme stage in the evolution of the most massive stars. Most stars never reach the hypergiant phase because they simply lack sufficient mass. Only stars with initial masses above roughly 20 to 25 solar masses can evolve into hypergiants, and even then, only under particular conditions. Many massive stars explode as supernovae while still in the blue supergiant phase. Only some progress into red supergiants, and only a small fraction of those go on to become hypergiants. For that reason, Stephenson 218 stands out as a rare and remarkable object. It offers a glimpse into the most extreme end of stellar evolution, a star that has pushed the boundaries of size to their limits. Now, let us return to the visualization we began with. Imagine standing on Earth, looking up into the night sky. Now picture a completely different scenario, where instead of the Sun, Stephenson 218 occupies the center of our solar system. The appearance of the sky would be entirely transformed. During the daytime, you would not see a bright, concentrated point of light overhead. Instead, you would observe an enormous, dim, red disk stretching across a large portion of the sky. The surface of the star would be so close that it would appear as a vast disk rather than a distant point. And because you would actually be inside the outer layers of the sky would be filled with glowing gas in every direction. Of course, in reality, Earth could not survive under such conditions. The planet would have been vaporized long before, as the star expanded outward. But if we imagine, hypothetically, a platform suspended in space at the distance where Earth typically orbits, about 1 astronomical unit from the center, that location would lie deep within the star's atmosphere. Temperatures would reach thousands of degrees. The pressure would be immense beyond comprehension. You would be immersed in a sea of luminous plasma. Looking outward, you would notice a gradual increase in brightness toward the core of the star, and a fading glow toward its outer regions. There would be no sharp edges, no clear sense of direction, no up or down, only an endless expanse of glowing gas surrounding you in every direction. In many ways, it would resemble a vision of hell, a place completely hostile to anything that resembles life or structure. And yet, paradoxically, it is also a place where creation is taking place. This is where heavy elements are formed, where the raw ingredients for future planets and future life are produced. The very processes that make this environment so deadly are also the ones that allow the universe to develop complexity. Nuclear fusion occurs in the core. Convection currents move material through the outer layers. Stellar winds drive mass away from the star. Eventually, a supernova explosion will scatter enriched material across vast distances measured in light years. These processes are not purely destructive. They are also constructive. They are the mechanisms through which the universe builds the chemical foundation for everything that follows. Stevenson 218 will not endure forever. Within a few million years, perhaps even within the next million years, it will undergo a catastrophic explosion. When that happens, the event will be visible from Earth. A brilliant new star will appear in the constellation Scutum. For weeks or even months, it will outshine most of the stars in the night sky before slowly fading away. The remnant of the explosion will expand outward, eventually forming a nebula that may remain visible for thousands of years. Over time, that nebula will gradually disperse into the surrounding space. The elements created within the star and during the explosion will mix with the interstellar medium. New stars will form from this enriched material. Some of those stars will have planetary systems. Some of those planets may eventually develop life. And if that happens, that life will owe part of its existence to Stevenson 218. The carbon within its molecules, the oxygen in its atmosphere, the iron in its core, all of it will have been forged in stars like this one. This is the legacy of hypergiants. They do not leave behind stable systems or long-lasting structures. Instead, they leave behind enriched material, the seeds from which future complexity can grow. Now, before we conclude, consider what Stevenson 218 represents for our understanding of the universe. This star challenges our models of stellar evolution. Objects of this size should not remain stable according to our theories, and yet they clearly exist. In principle, these stars should tear themselves apart under the force of their own radiation pressure, and yet they remain intact, at least for some time. Studying objects like these allows us to sharpen our theories. They reveal the extremes, the boundary conditions where our models are pushed to their limits. Each time we observe a hypergiant, we gather more information, placing tighter constraints on the physics involved. And even so, there is still much that remains unclear. We do not yet have a complete understanding of how mass loss works. How exactly does a hypergiant expel material through stellar winds? What mechanisms actually drive those outflows? How much mass is truly lost throughout the lifetime of such a star? We also lack a full understanding of their internal structure. What processes are unfolding deep in the core? How does convection behave in an object that is both enormous and diffuse? Are there distinct layers or shells composed of different elements? And then there is the question of the final outcome. Will Stevenson 218 explode as a typical supernova, or will it lead to something far more unusual? Could it collapse directly into a black hole without producing any visible explosion at all? These questions remain open, and the only way to approach answers is through continued observation, improved instruments, and ever more refined models. Stevenson 218 represents a single data point within a much larger effort to understand how stars function. Yet, it is a crucial one because it lies at the extreme end. And by studying the extremes, we gain insight into the full spectrum of stellar behavior. If we limited ourselves to stars like the Sun, our understanding would remain incomplete. We must examine the smallest stars, the largest ones, the hottest, the coolest, the youngest, and the oldest. Every category reveals something unique. Hypergiants, in particular, teach us about limits. How large can a star grow? How bright can it become? How unstable can it be? What happens when the laws of physics are pushed to their breaking point? Stevenson 218 offers partial answers to some of these questions, while at the same time raising entirely new ones. Now, consider what makes red hypergiants especially fascinating. These stars exist within a very brief and specific stage of evolution. They are massive stars that have already exhausted the hydrogen fuel in their cores and have begun fusing heavier elements, yet they have not reached the final phase that leads to a supernova. They are in a transitional state, and that transition produces unique physical conditions. At the core of a red hypergiant, contraction and heating occur as helium is fused into carbon and oxygen. This contraction releases gravitational energy, which in turn heats the surrounding layers. Those outer layers respond by expanding dramatically. It may seem counterintuitive, but this is how stellar physics operates. A contracting core leads to an expanding outer envelope. The envelope expands so much that it cools significantly. The surface temperature drops from tens of thousands of degrees, typical of a massive main sequence star, down to only a few thousand degrees in a red hypergiant. This cooling causes the star to appear red instead of blue or white. Despite this lower surface temperature, the total energy output actually increases. The star becomes more luminous because its surface area grows enormously. Think of it this way. A small, extremely hot piece of metal emits a certain amount of energy. A much larger, warm piece of metal can emit far more total energy, even though each part of it is cooler. This is exactly what happens with red hypergiants. The energy emitted per unit area is lower, but the total surface area is so vast that the overall output becomes immense. Another striking feature of these stars is their instability. Red hypergiants are not stable objects. They pulsate, their brightness fluctuates, and they lose mass in an irregular manner. Their outer envelopes are so weakly bound that material is constantly escaping into space. Powerful stellar winds carry away matter at rates that would alarm any engineer attempting to design a stable system. Some estimates suggest that Stephenson 218 may be losing mass at a rate of about 1/10,000th of a solar mass per year. That figure may sound small, but over the span of 1,000,000 years, it amounts to 100 solar masses, more mass than many entire stars possess. This continuous mass loss has major consequences. The star is gradually shrinking as it sheds its outer layers. At the same time, the surrounding region becomes filled with material that has already been expelled. This forms a circumstellar envelope, a cloud of gas and dust encircling the star. When we observe Stephenson 218, we are not seeing only the star itself, but also this surrounding material. That makes precise measurements more challenging, since we must account for the contribution of the circumstellar environment. Part of this material is driven outward by radiation pressure. Photons emitted by the star collide with dust particles and atoms in the envelope, transferring momentum. This pressure pushes the material outward, generating a stellar wind. However, the flow is not smooth or steady. It is clumpy, variable, and irregular. Observations indicate that red hypergiants can host enormous convection cells on their surfaces. These motions are vast, rising and sinking flows of hotter and cooler gas, much like the convection observed in boiling water, but occurring on a scale that is almost impossible to imagine. A single convection cell can be larger than the entire path of Earth's orbit around the Sunday. These enormous cells generate regions of higher temperature and lower temperature across the star's surface. As the star turns on its axis, which it does, though at a slow pace, these regions shift in and out of our line of sight. This leads to changes in brightness that can be detected and measured from Earth. By analyzing these fluctuations, astronomers are able to determine the star's rotation speed, examine the structure of its surface, and better understand the physics of convection under such extreme conditions. Another contributor to variability comes from pulsations. The star undergoes cycles of expansion and contraction over spans of months or even years. When it expands, its outer layers move outward, its size increases, and its temperature drops slightly. When it contracts, the reverse occurs. These pulsations are driven by the Kappa mechanism, a feedback process in which increased opacity in the outer layers causes them to trap more radiation, heat up, expand, then cool and shrink again. It behaves like a natural oscillation, similar to a spring moving up and down. For Stephenson 218, these pulsations may alter the star's radius by about 10 or 20% over a period of 1 or 2 years. This means the star could range from roughly 1,800 solar radii to 2,200 solar radii during a pulsation cycle. Measuring these changes allows astronomers to probe the star's internal structure, since the pulsation period is linked to its mass, radius, and internal density distribution. Now, consider the star's magnetic field. Most stars possess magnetic fields generated by dynamo processes within their interiors. The Sun, for example, has a magnetic field responsible for sunspots, solar flares, and coronal mass ejections. Red hypergiants are also expected to have magnetic fields, although detecting them is far more challenging because of their great distances. In a red hypergiant, the magnetic field is influenced by both rotation and convection. As the convective cells move up and down, they carry magnetic field lines with them, creating intricate and tangled magnetic patterns. These magnetic fields may play a role in driving the loss of mass from the star. They could guide material away along magnetic field lines, much like how the Sun's magnetic field directs the solar wind. They might also form hotspots where energy becomes concentrated, heating specific areas of the star's atmosphere. These localized regions could help explain the X-ray emissions observed in some red hypergiants. Although X-rays from a cool star may seem unexpected, magnetic activity can generate small pockets of extremely hot plasma even within an otherwise cool stellar environment. The study of magnetic fields in red hypergiants remains an active and evolving field. Improved instruments, especially spectropolarimeters capable of detecting the polarization of light caused by magnetic fields, are enabling astronomers to map these structures in greater detail. Each new observation deepens our understanding of how these extraordinary stars function. Let's look at some concrete comparisons to better grasp the immense scale involved. Stephenson 218 has a radius of approximately 930 million miles. To understand this more clearly, we can express it in different units. In astronomical terms, that is about 10 astronomical units. 1 astronomical unit represents the distance between Earth and the Sun, which is roughly 93 million miles. So, the radius of this star alone is about 10 times the Earth-Sun distance. Its full diameter is therefore close to 20 astronomical units. Neptune, the most distant planet in our solar system, orbits at around 30 astronomical units from the Sunday. If Stephenson 218 were placed at the center of our solar system, its surface would extend far beyond Neptune's orbit. Pluto, the dwarf planet, orbits at an average distance of about 39 astronomical units, meaning even Pluto would lie within the star. The Kuiper Belt, a region filled with icy bodies beyond Neptune, begins near 30 astronomical units and stretches out to roughly 50 astronomical units. This region would remain outside the star's surface, while anything within about 10 astronomical units would be completely swallowed. Now, think about this in terms of time. Light moves at approximately 186,000 miles per second. In just 1 second, light can circle Earth's equator about 7.5 times. It takes light about 8 minutes and 20 seconds to travel from the Sun to Earth. But how long would it take light to cross the diameter of Stephenson 218? The diameter is roughly 1,860,000,000 miles. With light traveling at 186,000 miles per second, dividing 1,860,000,000 by 186,000 gives about 10,000 seconds. That is roughly 2 hours and 47 minutes. In other words, light would need about 2 hours and 47 minutes to travel from one side of Stephenson 218 to the other. By comparison, light takes only about 4.6 seconds to cross the diameter of the Sunday. Or take Earth as a reference, where light requires roughly 0.042 seconds to travel from one side to the other. This star, however, is so immense that even light, the fastest entity in the universe, needs more than 6 hours to cross its full diameter. If you could somehow find yourself at the center of Stephenson 218 and send out a beam of light toward its surface, that signal would take about 1 hour and 24 minutes to arrive. By the time it reached the outer layers, the conditions there could already have shifted dramatically within the star's constantly changing atmosphere. Another way to understand its scale is by considering its mass. We've established that Stephenson 218 contains about 12 to 16 times the mass of the Sunday. The Sun itself has a mass of approximately 2 times 10 to the 30 kilograms. That's a 2 followed by 30 zeros, and it equals about 330,000 times the mass of Earth. Based on this, Stephenson 218 holds somewhere between 24 and 32 times 10 to the 30 kilograms. In other words, that corresponds to roughly between 4 million and 5,300,000 Earths. Yet, this enormous mass is distributed across a volume about 10 billion times larger than that of the Sunday. As a result, its average density is about 1 billion times lower than the Sun's. The Sun has an average density of around 1.4 grams per cubic centimeter, slightly denser than water. In contrast, Stephenson 218 has an average density of about 0.000014 grams per cubic centimeter, which is 14 millionths of a gram per cubic centimeter. To put that into perspective, the best vacuum we can produce in laboratories on Earth reaches about 1 trillionth of a gram per cubic centimeter. So, although the star's average density is still thousands of times higher than a laboratory vacuum, it remains extraordinarily low when compared to typical stellar matter. Its core would be significantly denser, potentially matching or even exceeding the density found in the Sun's core. However, its outer layers are incredibly diffuse, almost empty by any standard we experience on Earth. Now, let's look at the historical background behind the discovery of red hypergiants. For most of human history, stars were believed to be fixed, unchanging points of light. The ancient Greeks referred to them as the fixed stars, setting them apart from the wandering stars, which we now call planets. It wasn't until the Renaissance that astronomers began to realize that stars could change over time. In 1572, Tycho Brahe observed a new star appearing in the constellation Cassiopeia. At its brightest, it outshone Venus and was even visible during daylight. This event was a supernova, although that term would not be introduced until much later. In 1604, Johannes Kepler witnessed another supernova in the constellation Ophiuchus. These discoveries challenged the long-held belief that the heavens were unchanging. Still, the true nature of stars remained unclear. Were they suns like our own? Were they fundamentally different objects, and how far away were they located? These questions were not fully answered until the 19th and 20th centuries. The introduction of spectroscopy in the mid-1800s transformed astronomy. By separating starlight into its individual colors, scientists were able to determine the chemical composition of stars. Each element absorbs and emits light at specific wavelengths, producing unique spectral signatures. This method revealed that stars are composed primarily of hydrogen and helium, the same basic elements found on Earth, though in very different proportions. It also showed that stars vary in temperature, with hotter stars appearing blue and cooler stars appearing red. In the early 1900s, astronomers Ejnar Hertzsprung and Henry Norris Russell independently created what is now known as the Hertzsprung-Russell diagram. This diagram plots a star's luminosity against its temperature. When thousands of stars are mapped onto this graph, clear patterns emerge. Most stars lie along a diagonal band called the main sequence, where our Sun is located. However, some stars fall outside this region. These include giants and supergiants, which are far more luminous than main sequence stars with similar temperatures. Red giants and red supergiants are found in the upper right portion of the diagram, where luminosity is high but temperature is relatively low. As telescope technology improved and surveys catalogued more stars, astronomers discovered that this region extends to extremely high luminosities. Some stars are so bright that they overshadow nearly everything around them. These exceptionally luminous, cool stars were eventually classified as hypergiants. The term hypergiant was introduced to distinguish them from ordinary supergiants. They are not just larger, they represent an entirely different level of extremity. Early examples of such stars included VV Cephei, identified in the 1930s as a red supergiant with a massive radius. Mu Cephei, also known as Herschel's garnet star due to its deep red appearance, was another well-known early example. VY Canis Majoris was once considered the largest known star, with estimates in the 1990s suggesting a radius of up to 2,800 solar radii. Later measurements revised that figure downward to around 1,420 solar radii. Although still enormous, it was not as large as initially believed. This pattern of revising measurements is a common feature in astronomy. As our instruments become more advanced and our methods continue to improve, the precision of our measurements steadily increases. Early estimates often come with significant uncertainties, and in many cases, the true values end up differing from those first approximations. UY Scuti was once considered a major contender for the title of the largest known star. Although it was discovered back in the 1860s, it wasn't until the development of modern infrared observations that its actual scale began to be properly understood. Early calculations suggested it could have a radius as large as 1,900 solar radii. More recent measurements, however, place it closer to about 755 solar radii. Stephenson 2-18 joined this competition much later. The cluster it belongs to was identified in 1990, but detailed analysis of the individual stars within that cluster came afterward. It wasn't until the 2000s and 2010s that high-resolution infrared observations enabled astronomers to accurately determine the characteristics of stars in that region. Based on those observations, Stephenson 2-18 emerged as one of the strongest candidates for the largest star ever discovered. Its immense size, along with relatively reliable measurements, places it at or near the very top of the list. But this competition is far from settled. Astronomy is always evolving. New discoveries are constantly being made, earlier measurements are refined, and rankings can shift over time. What we can say for now is that Stephenson 2-18 stands among the largest stars ever identified, and it may very well be the largest. Future observations will continue to improve our understanding and may adjust that conclusion. Now, consider the technology that makes it possible to study stars like this. Observing Stephenson 2-18 requires specialized tools. Traditional optical telescopes struggle because the star is heavily obscured by interstellar dust. The cluster lies within the galactic plane, the disk of the Milky Way, where most of the galaxy's gas and dust are concentrated. Between us and Stephenson 2, there is a substantial amount of intervening material. This material tends to absorb blue and green light more strongly, while allowing red light to pass through more easily. That is why certain regions of the night sky appear darker than others, and why the Milky Way band is marked by dark lanes and bright patches. Those dark streaks are clouds of dust blocking the light from stars located behind them. To penetrate this dust, astronomers rely on infrared telescopes. Infrared light has longer wavelengths than visible light, which makes it less affected by dust. The same dust grains that block visible light are often transparent to infrared radiation. Several major infrared observatories have contributed to the study of Stephenson 2-18. The Infrared Astronomical Satellite, launched in 1983, was among the first space-based infrared telescopes. It conducted a full sky survey in infrared, detecting hundreds of thousands of sources, including many cool and dusty stars. Data from IRAS helped identify the Stephenson 2 cluster as an area worth investigating. The 2 mass, carried out in the late 1990s and early 2000s, mapped the entire sky in near-infrared wavelengths. Its data provided more precise positions and brightness measurements for stars within the cluster, allowing astronomers to begin identifying individual members more clearly. The Spitzer Space Telescope, launched in 2003, delivered even more detailed infrared images and spectra. It could observe at longer wavelengths than earlier missions, enabling it to detect cooler dust and peer deeper into obscured regions. Spitzer's observations played a key role in understanding the dust surrounding stars like Stephenson 2-18. The Herschel Space Observatory, which operated from 2009 to 2013, extended observations even further into the far infrared and submillimeter range. It was capable of detecting the coldest dust and gas, helping map the material surrounding stars in unprecedented detail. Ground-based infrared telescopes have also been essential. The Very Large Telescope in Chile, operated by the European Southern Observatory, includes multiple instruments designed for infrared observations. Its large mirrors and location in the Atacama Desert, one of the driest places on Earth, make it especially well suited for this kind of work. Similarly, the Keck Observatory in Hawaii, home to 2 of the largest optical and infrared telescopes in the world, has also been used to study stars in the Stephenson 2 cluster. These telescopes employ adaptive optic systems, which compensate for atmospheric turbulence in real time, allowing for much sharper images. Adaptive optics works by using a deformable mirror that adjusts its shape hundreds of times per second to correct distortions caused by Earth's atmosphere. This enables ground-based observatories to achieve image quality close to that of space telescopes, especially at infrared wavelengths where atmospheric interference is less severe. Spectroscopy is essential for understanding stars like these. By splitting the light from a star into its spectrum and examining which wavelengths are present, astronomers can determine its temperature, chemical composition, velocity, and many other important properties. High-resolution spectrographs, which are instruments designed to generate extremely detailed spectra, are capable of identifying absorption lines associated with particular elements and molecules. These spectral signatures reveal the chemical composition of a star. In the case of Stephenson 218, spectroscopic analysis shows the presence of molecules such as titanium oxide and water vapor within its atmosphere. These types of molecules can only persist at comparatively low temperatures, confirming that the star belongs to the category of cool hypergiants. Spectroscopy is also used to determine radial velocity, meaning how quickly the star is moving toward us or away from us. This is achieved by measuring the Doppler shift of its spectral lines. When the star is approaching, its light is blue shifted, meaning the wavelengths become slightly shorter than they would be if the star were not moving. When it is receding, the light is redshifted, and the wavelengths are slightly longer. The magnitude of this shift directly indicates the star's velocity. For Stephenson 218, radial velocity data helps verify that it is part of the Stephenson 2 cluster. The stars in that cluster are expected to share similar radial velocities because they are traveling together through space. Photometry, which involves measuring brightness over time, reveals variability in the star's output. Automated survey telescopes repeatedly scan the sky, compiling light curves that track how a star's brightness changes over time. For variable stars such as Stephenson 218, these light curves show both the timescales and the magnitude of variation. Does the star pulse in a regular pattern or in an irregular one? How significant are the changes in brightness? These observations help constrain theoretical models describing the star's internal structure and behavior. Interferometry is a method that combines light collected from multiple telescopes in order to achieve a level of resolution far beyond what a single telescope can provide. By precisely measuring the phase differences of light waves arriving at separate telescopes, astronomers can reconstruct images with a resolution equivalent to that of a telescope whose size matches the distance between those instruments. The Very Large Telescope Interferometer (VLTI) has been used to determine the angular diameters of certain nearby red supergiants. When these measurements are combined with distance estimates, they provide direct calculations of the star's physical size. For extremely distant objects like Stephenson 218, interferometry becomes much more difficult because their angular size is incredibly small. However, future interferometer arrays with longer baselines may eventually resolve such stars directly. This would allow for a direct measurement of the star's size, greatly reducing the uncertainties present in current estimates. Now, let us examine what occurs after a red hypergiant undergoes a catastrophic explosion. The resulting event will be a Type II supernova, which happens when the core of a massive star collapses. The process unfolds as follows. The star has been fusing progressively heavier elements in its core, hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, and so on. Each successive stage produces less energy and proceeds more rapidly than the previous one. Eventually, the core begins fusing silicon into iron. This final phase lasts only a few days. Iron represents the most stable atomic nucleus. Attempting to fuse iron into heavier elements does not release energy. Instead, it requires energy input. As a result, once the core is composed primarily of iron, fusion ceases. At this point, the core is supported against gravitational collapse only by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed too closely together. However, there is a maximum mass that electron degeneracy pressure can support, known as the Chandrasekhar limit. For an iron core, this limit is approximately 1.4 solar masses. When the core exceeds this threshold, electron degeneracy pressure is no longer sufficient to counteract gravity. The core collapses, and it does so extremely rapidly. In less than a second, a core roughly the size of Earth contracts into a sphere only about 20 miles across. The density rises to nuclear levels approximately 100 trillion times the density of water. Under these extreme conditions, electrons are forced to merge with protons, forming neutrons and releasing vast numbers of neutrinos. The core transforms into a neutron star, an object so dense that a single teaspoon of its material would weigh around 1 billion tons. The collapse happens so quickly that the outer layers of the star cannot respond in time. They continue falling inward even as the core reaches nuclear density and abruptly halts its collapse. The infalling material then collides with the newly formed, extremely dense core and rebounds outward. This rebound generates a powerful shock wave that travels through the star. The shock wave carries immense energy, heating the outer layers to billions of degrees, which is sufficient to trigger explosive nucleosynthesis. Elements heavier than iron, which cannot be formed through standard fusion processes, are created during this explosive phase. Gold, platinum, uranium, and other heavy elements are synthesized in this brief interval of extreme physical conditions. The shock wave then propels the outer layers of the star into space at velocities ranging from 10,000 to 30,000 miles per second. This expelled material expands outward, forming a structure known as a supernova remnant. The leftover core shines intensely as the outgoing shock wave heats the gas around it. Seen from Earth, this supernova would show up as a newly appeared bright star in the constellation Scutum. It would emerge suddenly in a place where no prominent star existed before, potentially reaching a brightness of -7 or -8 magnitude. That is even brighter than Venus, luminous enough to be visible in daylight. It would stay brilliant for several weeks, then slowly dim over the course of months. The light curve, which tracks brightness over time, would display a rapid initial increase as the shock wave reaches the surface, followed by a peak when the greatest amount of material is heated, and then a gradual fading as the expanding remnant cools and becomes more transparent. This fading phase would be driven by the decay of radioactive elements formed during the explosion, especially nickel, 5,6, which transforms into cobalt, 5,6, and eventually into iron, 5,6. This radioactive process supplies energy that allows the remnant to continue glowing for months after the initial blast. Neutrinos, produced during the collapse of the core, carry away most of the energy from the explosion, roughly 99% of it. These particles interact only weakly with matter and escape almost instantly, streaming outward from the core at nearly the speed of light. Only about 1% of the energy contributes to the visible explosion, yet even that small fraction is enormous. A typical Type II supernova releases around 10 to the 46 joules of energy as kinetic motion and light. That amount is about 100 times the total energy the Sun will emit over its entire 10 billion year lifetime, released within just a few seconds. The explosion would hurl approximately 10 to 15 solar masses of material into space. This matter, enriched with heavy elements forged both within the star and during the supernova itself, would blend into the interstellar medium. Over millions of years, it would cool and condense, eventually forming new clouds of gas and dust. These clouds could collapse to give birth to new stars. Those stars would contain slightly higher metal content than Stephenson 218, continuing the long process of chemical enrichment that has been underway since the first stars formed. What remains at the core would either be a neutron star or a black hole. If it becomes a neutron star, it could be observed as a pulsar, a rapidly spinning neutron star that emits beams of radiation. As it rotates, these beams sweep across space like lighthouse beams. If one of these beams happens to align with Earth, we detect regular pulses of radio waves, which is why it is called a pulsar. Pulsars can rotate at incredible speeds, with some spinning hundreds of times each second. They are extremely dense objects, with magnetic fields trillions of times stronger than Earth's, making them among the most extreme objects in the universe. Studying them reveals physics under conditions that cannot be recreated in any laboratory. If the core is too massive to be supported by neutron degeneracy pressure, it collapses further into a black hole. A stellar mass black hole formed from a star like Stephenson 218 might have a mass of about 10 to 15 solar masses. Its event horizon would measure only about 60 to 90 miles across, incredibly small compared to the original star, yet containing all the mass of the collapsed core. Black holes formed from stellar collapse are often found in binary systems, orbiting a companion star. If that companion star is close enough, the black hole can pull matter away from it, creating an accretion disk. Material in this disk spirals inward, heating to millions of degrees and emitting X-rays. These X-ray binary systems rank among the brightest X-ray sources in the galaxy. They are easier to detect than isolated black holes because the infalling material glows so intensely. Isolated black holes, by definition, emit no light, making them extremely difficult to find unless they pass in front of a distant star and bend its light through gravitational lensing. The expanding supernova remnant would move outward at thousands of miles per second. Over thousands of years, it would grow to span dozens of light years. Eventually, it would fade as the material disperses and cools. Some well-known supernova remnants include the Crab Nebula, which comes from a supernova observed in 1054 AD. The Crab Nebula is powered by a pulsar at its center, rotating 30 times per second and feeding energy into the surrounding nebula. Cassiopeia A is another famous remnant, produced by a supernova that occurred around 1680, though it was not seen at the time due to heavy dust obscuration. These remnants act as natural laboratories for studying supernova processes, shock waves, and the interaction between ejected material and the interstellar medium. One day, the remnant of Stephenson 218 will join this group. it will become another expanding shell of enriched gas, shining in radio waves and X-rays, gradually mixing with the galaxy's interstellar medium. Another important aspect to consider is the presence of dust around such stars. Red hypergiants are enveloped by dense clouds of dust that they have expelled over millions of years. This dust is produced when material in the outer layers of the star cools sufficiently for molecules to condense into solid particles. In the intensely hot inner regions near the star, temperatures are far too high for dust to survive. Gas becomes ionized. Atoms are torn apart. However, as you move farther away from the star, the temperature begins to fall. At a few thousand degrees, molecules are able to form. Water, carbon monoxide, titanium oxide, and others appear as you travel even farther outward. Temperatures decrease below a few thousand degrees. Under these conditions, solid particles can condense from the gas. Silicate grains, carbon grains, iron grains, depending on the chemical composition and the local temperature and pressure. These particles are extremely small, typically only a fraction of a micron in size, far smaller than a grain of sand. Yet together they build dense clouds that can completely hide the star at visible wavelengths. The dust absorbs visible and ultraviolet radiation from the star, warms up, and then re-emits that energy in the infrared. This is why dusty stars shine brightly in infrared observations, even if they appear dim in visible light. The energy has not disappeared, it has simply shifted to longer wavelengths. Radiation pressure from the star pushes these dust grains outward. Photons from the star strike the grains and transfer momentum, producing an outward force. For very small particles, this force can exceed gravity, driving them away from the star. As these grains drift outward, they pull surrounding gas along through collisions. This process creates a dusty wind, a steady flow of gas and dust moving away from the star. The wind carries away material, gradually peeling off the star's outer layers. Over time, the star loses a considerable portion of its mass through this mechanism. For Stephenson 218, the surrounding dust shell extends across many stellar radii. It may reach tens or even hundreds of astronomical units from the star. This dust is what makes the star appear extremely luminous in infrared surveys. Observatories such as Spitzer and Herschel have detected vast quantities of cool dust around it, far more than expected for a star without strong mass loss. This dusty envelope is direct evidence that the star is actively losing mass and moving closer to its final stages. The more dust present, the more material the star has already shed, and the nearer it likely is to becoming a supernova. When that supernova eventually occurs, the resulting shock wave will collide with this surrounding material. The impact will heat the gas and dust to extremely high temperatures, causing them to shine intensely in X-rays and visible light. This interaction between the supernova ejector and the circumstellar environment can persist for years or even decades after the explosion. It forms a bright, expanding shell that can be easier to observe than the later supernova remnant itself. Some supernovae display clear signs of this process in their light curves. The brightness first peaks due to the explosion, then shows a later rise or plateau as the ejector interact with surrounding material. By analyzing these patterns, astronomers can reconstruct the mass loss history of the original star, determining how much mass it expelled and when that loss occurred. Now, consider the ultimate destiny of the matter within Stephenson 218. At present, The star contains about 12 to 16 solar masses of material. Most of this is hydrogen and helium, the most abundant elements in the universe. However, it also includes a notable fraction of heavier elements, such as carbon, nitrogen, oxygen, and others. These heavier elements were forged in earlier generations of stars and became part of the cloud from which Stephenson 218 was born. Throughout its lifetime, nuclear fusion in the core has produced even more heavy elements. Helium transforms into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. The internal structure resembles layers of an onion, with an iron core surrounded by shells of silicon, oxygen, and other elements extending outward. When the supernova takes place, the explosion will generate additional heavy elements through explosive nucleosynthesis. Elements heavier than iron, which cannot form through ordinary fusion, are created during the brief, intense conditions of the supernova event. All of this enriched material, approximately 10 to 15 solar masses, will be expelled into space. It will mix with the interstellar medium, becoming part of the galaxy's supply of gas and dust. Eventually, that material will collapse again to form new stars. Some of those stars will host rocky planets composed of elements that were once inside stars like Stephenson 218. And if any of those planets give rise to life, that life will be built from atoms that were once part of Stephenson 218. This is the cosmic cycle of matter. Stars forge heavy elements, disperse them into space, and new stars and planetary systems emerge from that enriched material. Over billions of years, the galaxy becomes increasingly rich in heavy elements. Each new generation of stars contains slightly more of these elements than the one before. Earth and the Sun came into existence around 4.6 billion years ago, emerging from a cloud of gas and dust that had already been enriched with heavy elements produced by earlier generations of stars. The iron at the center of Earth, the oxygen we breathe in the atmosphere, the carbon that forms the basis of our bodies, all of these elements originated in stars that lived and died long before the Sun ever formed. And far into the future, after the Sun reaches the end of its life and releases its outer layers into space, those same atoms may once again become part of new stars and new planets, perhaps even new forms of life. Matter does not disappear. It is continually recycled across the universe. Stephenson 218 belongs to that ongoing cycle, representing a short yet dazzling stage in the long journey of matter through the cosmos. Before we finish, it is worth reflecting on just how extraordinary it is that we are able to study such objects at all. Stephenson 218 lies about 19,000 light-years away, a distance so immense that it is almost impossible to truly grasp. If you were to travel there at the speed of a commercial airplane, roughly 600 miles per hour, the journey would take around 21 billion years, which is longer than the current age of the universe itself. Even at the speed of the Voyager spacecraft, about 38,000 miles per hour, the trip would still require about 340 million years. There is no realistic way for us to physically reach this star. No spacecraft that we can currently imagine could complete such a journey within a human lifetime, or even within the entire span of human civilization. And yet, despite that impossibility, we can still study it in remarkable detail. We can determine its size, its surface temperature, its brightness, and its chemical makeup. We can observe how it changes over time, monitor its variability, and even map aspects of its structure. We can make predictions about when it will eventually explode and what the consequences of that event will be. All of this knowledge comes from light that has traveled 19,000 years across space to reach us. These photons left the star at a time when humans were still living in small groups, hunting and gathering, long before the invention of writing, agriculture, or cities. Those photons have spent all that time crossing the galaxy, passing through clouds of gas and dust, until finally arriving at Earth and entering our telescopes. From those tiny packets of light, we are able to reconstruct the entire life story of a star that spans about 2 billion miles in diameter. That is the true power of astronomy. It is also the power of science itself. From faint signals, subtle patterns, and tiny traces of information carried by light, we assemble a coherent picture of the universe. We uncover how stars are formed, how they evolve, and how they ultimately die. We discover the physical laws that govern everything, from the smallest particles to the largest cosmic structures. And we achieve all of this from a small planet orbiting an ordinary star in a galaxy that is not particularly special. This is one of humanity's greatest accomplishments, not the construction of monuments or the conquest of land, but the pursuit of understanding. Understanding how the universe operates, understanding our place within it, understanding where we come from and where we are heading. Stevenson 218 stands as a powerful example of that understanding. A star we will never touch, yet we can examine. A star we will never visit, yet we can know. A star that exists in an extreme realm, almost beyond imagination. And still, we can measure it, analyze it, and make sense of it. Now, consider some of the practical difficulties astronomers encounter when observing stars such as Stevenson 218. One of the most significant challenges comes from the interference caused by Earth's atmosphere. The atmosphere is never still. It is constantly shifting, with layers of air at different temperatures moving in complex patterns. These motions create turbulence, which causes starlight to bend slightly as it passes through regions of varying density. To the naked eye, this produces the familiar twinkling of stars, something that appears beautiful but creates serious problems for astronomers who need precise measurements. The image of the star appears to wobble, blur, and shimmer. For distant stars, which appear as point sources, this results in twinkling. For objects that appear slightly larger, such as planets or nearby stars, it leads to a blurred image. Adaptive optic systems help reduce this problem to some extent. These systems measure distortions in real time using a reference source known as a guide star. This guide star can either be a naturally bright star located near the object being observed, or an artificial one created by projecting a laser beam into the upper atmosphere. The laser excites sodium atoms at an altitude of about 90 miles, producing a glowing point of light that acts like a star. By analyzing how the light from this guide star is distorted, the system determines the exact effects of the atmosphere at that moment. It then adjusts a flexible mirror inside the telescope, changing its shape hundreds or even thousands of times per second to counteract those distortions. This process greatly improves the clarity of the image, allowing ground-based telescopes to approach their theoretical resolution limits. However, adaptive optics works most effectively at infrared wavelengths. At visible wavelengths, the atmosphere changes too rapidly for the system to fully compensate in real time. So, even when using adaptive optics, observations made from the ground still face important limitations. Telescopes in space do not suffer from this issue because they operate above Earth's atmosphere. The Hubble Space Telescope, for example, can observe invisible wavelengths without any atmospheric distortion. However, Hubble was designed primarily for visible and ultraviolet light, not for infrared. Observing in the infrared requires specialized equipment. The James Webb Space Telescope, launched in December 2021, serves as a highly advanced infrared observatory. It features a significantly larger mirror than Hubble and is specifically optimized for infrared wavelengths. Webb is capable of detecting extremely faint and very cool objects that remain completely invisible to Hubble. It is expected that Webb will eventually observe Stephenson 2, 18, and other red hypergiants with an unprecedented level of detail. Its high-resolution infrared imaging could make it possible to directly measure the star's angular size, which, when combined with distance estimates, would yield an accurate physical radius. Webb's spectrographs could also examine the star's atmospheric composition in depth, identifying specific molecules and isotopes. This information would reveal important clues about the star's evolutionary path and the processes occurring deep within it. Another major challenge is determining distance. Knowing how far away a star is plays a crucial role in understanding its physical characteristics. Brightness alone is not enough, because a faint star nearby and a luminous star far away can appear equally bright when observed from Earth. Distance is needed to convert apparent brightness into true luminosity. For stars that are relatively close, within a few thousand light-years, astronomers rely on parallax. As Earth moves around the Sun, nearby stars appear to shift slightly relative to distant background stars. By measuring this small shift, astronomers can calculate distance using basic geometric principles. However, parallax is only effective for nearby stars. Beyond a few thousand light-years, the shift becomes too small to measure precisely. Even with advanced missions like Gaia, which has measured parallax for over 1 billion stars. For more distant stars, astronomers must use alternative techniques. If a star belongs to a cluster, the distance to that cluster can be estimated through various methods, and then it is assumed that all stars within the cluster lie at approximately the same distance. In the case of Stephenson 2, astronomers have applied multiple approaches. One is spectroscopic parallax, which uses the star's spectrum to determine its luminosity class and then compares its apparent brightness with its inferred true luminosity. Another is kinematic distance, which relies on the star's radial velocity and proper motion, meaning its motion across the sky, to estimate distance using models of galactic rotation. A third method involves analyzing the cluster as a whole. By identifying enough members and measuring their properties, astronomers can apply statistical techniques to estimate the cluster's distance. All of these methods involve uncertainties, which is why distance estimates for Stephenson 2 range from about 17,000 to 20,000 light-years. This uncertainty in distance directly affects estimates of the star's physical properties. For example, if the actual distance is 18,000 light-years instead of 19,000, the calculated luminosity would change, and this would alter the inferred radius. That is why radius estimates for Stephenson 218 are given as a range rather than a single exact value. More precise distance measurements would help reduce this uncertainty significantly. Now, let's examine what can be learned from the star's variability. As mentioned earlier, Stephenson 218 is a variable star, meaning its brightness changes over time. These variations provide valuable insight into the star's internal structure and behavior. The two primary causes of variability in red hypergiants are pulsations and surface convection. Pulsations are periodic expansions and contractions of the star. The entire star expands, then contracts, and then expands again. This occurs because of a feedback process in the outer layers of the star. When the star compresses slightly, the material becomes denser and hotter. Hotter material is more opaque, meaning it absorbs more radiation. This absorbed radiation heats the material further, causing it to expand. As it expands, it cools and becomes less opaque. Reduced opacity leads to less heating, so the expansion stops and gravity pulls the material inward again. This creates a repeating oscillation, similar to a spring being compressed and released. The duration of this oscillation depends on the star's size and mass. Larger stars have longer periods because pressure waves take more time to travel through them. For a star like Stephenson 218, the pulsation period could range from hundreds to thousands of days. By analyzing both the period and the amplitude of these pulsations, astronomers can place constraints on the star's mass and internal structure. Different theoretical models predict different pulsation patterns, so observations help refine and improve those models. Convection represents the second major source of variability. Inside a star, energy moves from the core outward to the surface through two primary processes: radiation and convection. In certain layers, radiation dominates. Photons slowly make their way outward, repeatedly scattering off atoms and gradually transporting energy toward the surface. In other layers, convection becomes the more effective mechanism. Hot material rises, while cooler material sinks, forming circulating currents that carry energy through the star. In red hypergiants, the outer layers are strongly convective. Enormous cells of rising hot gas and descending cooler gas spread across the surface. Each of these cells can be larger than the entire orbit of Earth around the Sunday. As these vast cells shift and change over time, the surface of the star becomes uneven and irregular. Some regions grow hotter and brighter, while others become cooler and dimmer. As the star rotates, these regions move into and out of view, leading to noticeable variations in brightness. If we could somehow observe Stephenson 218 up close, we would not see a smooth, uniform surface. Instead, we would witness a turbulent, boiling appearance, filled with enormous, bright and dark patches that are constantly changing and evolving. It would resemble the surface of vigorously boiling water far more than the calm, consistent surface of the Sunday. By tracking these variations over months and even years, astronomers can gradually build a detailed understanding of the star's surface behavior. How quickly do these convection cells change? How large are they? To what extent do they influence the overall brightness of the star? These questions provide insight into convection under conditions and scales that cannot be recreated in any laboratory on Earth. The Sun also exhibits convection in the form of granulation, but its cells are far smaller, typically around 600 miles across. In contrast, the convection cells on Stephenson 218 are hundreds of millions of times larger. Studying convection in such extreme stars improves our broader understanding of this process, which is important because convection plays a role in many areas of astrophysics, from planetary atmospheres to neutron stars. Now, let us consider the role of rotation. Stars rotate, and their rotation rates vary widely. The Sun completes one rotation approximately every 25 days at its equator, rotating more slowly at higher latitudes because it is composed of gas and different regions can move at different speeds. Massive stars on the main sequence often rotate much more rapidly, with some completing a full rotation in only a few hours. This rapid spin affects their structure, causing them to bulge at the equator and influencing how they evolve over time. Red hypergiants, however, rotate extremely slowly. As a star leaves the main sequence and expands, conservation of angular momentum might suggest that it should spin faster, similar to a figure skater pulling in their arms. Yet the opposite occurs. Red giants and hypergiants rotate more slowly than the stars they once were. This happens because they lose mass through powerful stellar winds, and that escaping material carries away angular momentum. As the star sheds its outer layers, it loses not only mass, but also rotational energy. The outcome is a swollen, slowly rotating star. Stephenson 218 likely completes a single rotation over several years, possibly even longer. This slow rotation has important consequences. It means the star remains nearly perfectly spherical with little to no equatorial bulging. It also means that rotation has minimal influence on the star's structure or its evolution at this stage. This is very different from massive main sequence stars, where rotation can play a major role. Rapid rotation can mix material between the core and the outer layers, bringing fresh fuel into the core and extending the star's lifespan. It can also generate strong magnetic fields and drive intense stellar winds. For Stephenson 218, however, rotation is only a minor factor. Its evolution is primarily governed by nuclear fusion, mass loss, and radiation pressure, rather than by rotation. This actually simplifies theoretical models because rotation introduces additional complexity. When a star rotates slowly, it can be treated as nearly perfectly spherical, making the mathematics much more manageable. Now let us place this star within the broader picture of massive star evolution. Stephenson 218 did not begin its life as a hypergiant. It formed as a massive main sequence star, likely a hot blue star with a mass tens of times greater than that of the Sunday. It spent several million years on the main sequence, fusing hydrogen into helium in its core. During this phase, it was extraordinarily luminous, perhaps 100,000 times brighter than the Sun, and extremely hot, with a surface temperature of 30,000 degrees Kelvin or higher. At that time, it was a blue supergiant rather than a red hypergiant. But once the hydrogen in its core was depleted, the star began to change. The core, now composed mostly of helium, contracted and grew hotter. This contraction released gravitational energy, heating the surrounding shell of hydrogen. That hydrogen shell then began to fuse, providing a new source of energy. In response to this additional energy, the outer layers of the star expanded. As they expanded, they cooled, and the star gradually shifted in color from blue to yellow and eventually to red. It became a red supergiant. But the process of evolution did not end at that stage. As the stellar core kept shrinking under its own gravity and its temperature continued to rise, helium fusion was eventually triggered in the core. This new stage of fusion generated even greater amounts of energy, pushing the outer layers outward and causing the envelope to expand further still. As a result, the star became both larger in size and cooler at the surface, ultimately transforming into a red hypergiant. At some stage, likely in the relatively near future when viewed on cosmic timescales, the star will run out of nuclear fuel. before that final moment, it may enter a last period of instability, possibly undergoing intense pulsations or expelling vast quantities of mass through powerful eruptions. Some red hypergiants already show clear signs of episodic mass loss, short-lived intervals during which they eject enormous amounts of material in outbursts that can last for months or even years. These violent events could be driven by instabilities within the extended envelope or by the ignition of additional fusion shells deep inside the core. Eventually, the core will collapse under gravity, leading to a supernova explosion that marks the end of the star's life. This entire evolutionary path from a main sequence star to a supernova unfolds over roughly 20 million years. By stellar standards, that is remarkably brief. For comparison, our Sun will remain on the main sequence for about 10 billion years before it begins its own transformation. Massive stars, in contrast, burn through their fuel quickly and end their lives early. Yet despite their short lifespans, their influence on the galaxy is profound. Through their intense stellar winds and their final supernova explosions, they enrich the interstellar medium with heavy elements. Their shockwaves compress nearby clouds of gas, helping to initiate the birth of new stars. In some cases, their radiation pressure and winds alone can trigger star formation by forcing surrounding gas to collapse. Many star-forming regions display clear evidence of this process, where the shockwave from a supernova or the radiation from massive stars compresses nearby gas and leads to the creation of new stellar systems. In this way, Stephenson 218, despite its relatively brief existence, plays a vital role in the broader ecology of the galaxy. It participates in an ongoing cycle of star formation, element production, and renewal that has continued for billions of years and will persist for billions more. Another important topic to consider is how different types of hypergiant stars compare to one another. Not all hypergiants are red. There are also yellow hypergiants and blue hypergiants, although they are even rarer than their red counterparts. Yellow hypergiants are believed to represent a very short transitional stage. These are stars that are either expanding from blue supergiants into red supergiants or contracting from red supergiants back toward blue supergiants. This transitional phase may last only a few thousand years, an incredibly short time even on stellar timescales. Because of its brevity, very few yellow hypergiants have been observed. One notable example is Rho Cassiopeiae, a star that has exhibited dramatic variability and episodes of mass loss. In 1998, it dimmed by about 1 magnitude over a period of a few months, likely due to the ejection of a large cloud of dust. Yellow hypergiants are highly unstable and occupy a region of the Hertzsprung-Russell diagram known as the yellow evolutionary void. This region appears sparsely populated because stars pass through it so rapidly that they are rarely observed there. At the opposite extreme are blue hypergiants. These stars are extraordinarily hot and luminous, with surface temperatures ranging from 20,000 to 50,000 degrees Kelvin. They rank among the brightest stars in the universe, sometimes outshining even red hypergiants. However, they are also rarer and less well understood. Examples include Rigel in the constellation Orion, which is sometimes classified as either a blue supergiant or a blue hypergiant, depending on the criteria used. Another well-known example is P Cygni, famous for its powerful stellar winds and distinctive spectral signatures. This star shows clear evidence of significant mass loss, with shells of previously expelled material surrounding it. Blue hypergiants are thought to be evolving very rapidly, potentially undergoing dramatic changes over timescales of centuries or thousands of years. They may represent stars on the verge of exploding as supernovae, or stars transitioning into another phase of stellar evolution. The precise relationships between blue, yellow, and red hypergiants are still not fully understood. Do all massive stars pass through each of these stages, or do some bypass certain phases entirely? Does a blue hypergiant inevitably evolve into a red hypergiant, or can it explode as a supernova while still in its blue state? These questions remain active areas of research. Observations of hypergiants in nearby galaxies, especially in the large and small Magellanic Clouds, have helped scientists make progress in answering some of these questions. The Magellanic Clouds are small satellite galaxies of the Milky Way. They are close enough that individual stars can be studied in detail, yet distant enough to provide a different environmental context. They differ in metallicity, star formation history, and overall conditions. By studying hypergiants in these galaxies and comparing them with those in the Milky Way, astronomers can better understand how factors like metallicity and environment influence stellar evolution. One significant conclusion is that metal-poor stars, those containing fewer heavy elements, tend to retain more of their mass and ultimately explode at higher masses. In contrast, metal-rich stars, such as those found in the Milky Way, lose more mass through stellar winds and therefore end their lives at lower masses when they explode. This has a direct impact on the kind of supernova they eventually produce and on the remnants they leave behind. Stars with low metallicity tend to end their lives as black holes. In contrast, stars rich in heavier elements are more likely to leave behind neutron stars. Stephenson 218, located within the Milky Way, possesses a metallicity close to that of the Sun, possibly even slightly higher. Its future evolution and ultimate fate will therefore be shaped by this composition. Now, let's turn to the deeper, more philosophical aspects of studying objects like Stephenson 218. Astronomy has never been purely scientific. It has always carried a philosophical dimension. When we look up at the night sky, we are naturally led to reflect on our place in the universe, on scale, on time, on existence itself. Stephenson 218 represents many of these profound questions. First, there is the issue of scale. Human beings evolved to understand sizes and distances relevant to survival, from meters to kilometers, from seconds to years. We are not naturally equipped to grasp billions of miles or spans of millions of years, and yet, through science, we have found ways to push beyond those limits. We are capable of understanding objects billions of times larger than anything we encounter in daily life. This is one of the great achievements of human thought. We are not confined by our senses or instincts. We create instruments that extend what we can perceive, telescopes that allow us to see farther into space, spectrographs that let us study light beyond the limits of human vision. We construct mathematical models to describe things we cannot observe directly. And through all of this, we gain insight into realities far removed from everyday experience. Second, there is the idea of impermanence. Stephenson 218 reminds us that nothing endures forever. Stars are born, they exist for a time, and then they die. Even the most massive and awe-inspiring stars have limited lifespans. And when viewed on cosmic timescales, those lifetimes are surprisingly short. 20 million years may seem immense to us. It exceeds the entire span of human civilization. It even surpasses the existence of our species. But compared to the universe's 13.8 billion year history, it is only a brief moment. This star will complete its life cycle in less than 1/5 of 1% of the current age of the universe. It is, in essence, a transient event. This impermanence applies to everything. Planets, galaxies, and even the universe itself will one day transform beyond recognition. In trillions of years, all stars will have exhausted their fuel. Galaxies will drift apart. The cosmos will become cold, dark, and nearly empty. Nothing we observe today will remain unchanged. Some people find this idea unsettling, while others see it as freeing. If everything is temporary, then the present moment becomes more meaningful. The fact that we exist right now, able to observe the universe in its current state, is extraordinary. We are fortunate to live in a time when stars still shine, when galaxies continue to form, and when the universe remains active and full of structure. Third, there is the idea of connection. Stephenson 218 lies 19,000 light-years away. We will never travel there. No human ever will, unless entirely new physics is discovered that permits faster-than-light travel. And yet, we are connected to it. The atoms that make up our bodies were forged in stars like this. The oxygen we breathe, the carbon in our DNA, the iron in our blood, all originated in massive stars that exploded billions of years ago. We are literally made of stardust, not as a poetic image, but as a physical reality. And when Stephenson 218 eventually explodes, it will disperse its enriched material into space. That material will later become part of new stars, new planetary systems, and perhaps even new forms of life. There is a vast cosmic cycle in motion, linking matter across space and time into a continuous process of transformation. We are part of that cycle. We are not separate observers standing outside the universe. We exist within it, composed of it, shaped by its history. This viewpoint, often referred to as the cosmic perspective, can be both humbling and empowering. Humbling because it reveals how small we are and how brief our lives are on cosmic scales. Empowering because it shows that we are part of something far greater than ourselves, part of a universe that has been evolving for billions of years and will continue to do so for billions more. Our lives carry meaning, not despite our smallness, but because we belong to this larger, unfolding story. Now, let us consider the future of research into red hypergiants. What discoveries might astronomers make in the years and decades ahead? Several advanced instruments and upcoming missions are set to transform our understanding of these stars. The James Webb Space Telescope, already in operation, will provide unprecedented observations in the infrared. Its high-resolution imaging may even allow astronomers to resolve the surfaces of nearby red supergiants, directly observing individual convection cells. For more distant objects, such as Stephenson 218, Webb will deliver highly detailed spectra, revealing information about atmospheric composition, temperature structures, and variability. The extremely large telescope, now being constructed in Chile, will feature a primary mirror measuring 39 meters across, making it the most powerful optical telescope ever created. Equipped with advanced adaptive optics, it will reach a level of resolution far beyond what current instruments can achieve. With this capability, it may even directly determine the angular diameter of Stephenson 218, allowing astronomers to calculate its size with remarkable precision. Meanwhile, the Square Kilometre Array, a massive radio telescope project underway in Australia and South Africa, will be sensitive enough to pick up faint radio signals emitted by stellar winds and the surrounding material of hypergiant stars. This will make it possible to map mass loss rates and wind structures in unprecedented detail. Future X-ray observatories will also contribute by examining the high-energy radiation coming from hypergiants, offering insights into their magnetic fields and the shock waves formed within their stellar winds. Missions such as Athena, the Advanced Telescope for High-Energy Astrophysics, planned for launch in the 2030s, will play a key role in this effort. Gravitational wave detectors, though primarily built to observe mergers of black holes and neutron stars, could also capture signals from supernova explosions. If Stephenson 218 eventually ends its life in such an explosion, next-generation detectors might register the gravitational waves produced by the collapsing core. This would open an entirely new window into supernova research, allowing scientists to probe directly into the core itself, rather than relying only on the light emitted by the expanding outer layers. At the same time, computer simulations are advancing rapidly. Modern supercomputers are now capable of modeling stellar evolution with extraordinary detail, following nuclear reactions, energy transport, and mass loss in full three-dimensional simulation. These models are uncovering new understanding of how convection behaves in the envelopes of hypergiants, how pulsations originate and spread, and what processes ultimately lead to their collapse. By comparing these simulations with observational data, astronomers can refine their theories step by step, gradually forming a more complete picture of these extreme stars. Let's end with a reflection on perspective. When you look up at the night sky, most of what you see are main sequence stars, ordinary stars, like our sun steadily fusing hydrogen. Hypergiants exist as well, but they are rare, and many are too distant or obscured to be visible without instruments. Stephenson 218 cannot be seen with the naked eye, hidden behind layers of dust and vast distances. But the fact that something is invisible does not mean it is absent. The universe is filled with phenomena beyond our direct perception, yet accessible through technology and understandable through science. Stephenson 218 exists at this very moment. About 19,000 light-years away, it glows as an immense object, far larger than anything we encounter in everyday experience. It shines, expands and contracts, sheds its mass, and moves steadily toward the end of its life. In a few million years, perhaps even sooner, it will explode. The light from that explosion will then travel across space for 19,000 years before reaching Earth. It will arrive in a distant future, long after everyone alive today is gone. Perhaps humanity will still exist, equipped with advanced telescopes to witness the event. Perhaps they will remember that their distant ancestors once studied this star, predicted its fate, and understood its nature. Or perhaps humanity will no longer be here, and the explosion will occur unseen, except possibly by other intelligent beings somewhere else in the galaxy. Either way, the explosion will take place. The laws of physics operate independently of observation. The star will complete its life cycle, dispersing enriched material into space and contributing to the ongoing evolution of the galaxy. That material will eventually become part of new stars, new planetary systems, and perhaps even new forms of life. The cycle continues without interruption. For now, we can observe Stephenson 218 from afar. We can measure it, study it, and interpret its behavior. We can appreciate its enormous scale, its relatively short lifespan, and its essential role within the broader cosmic system. And we can stand in awe of the fact that we, small beings on a modest planet, are capable of understanding something so vast and so distant. That is the strength of the human mind. That is the value of science. That is what allows us to grasp the universe we inhabit. Stephenson 218, the largest star ever identified, stands as evidence of the universe's ability to produce extremes. It is a star that pushes the boundaries of size, brightness, and instability. It is a star that challenges existing theories and broadens our knowledge. It is a star that reminds us of the immense scale and diversity of the cosmos. And it is a star that connects us to the larger story of how matter evolves across space and time. Thank you for being part of this journey exploring the largest star in the universe. If you found this exploration as compelling as I did, consider liking the video or subscribing to the channel. It helps bring these stories to others who share a curiosity about the cosmos. And remember, the next time you look up at the night sky, somewhere out there in the constellation Scutum, invisible to your eyes yet undeniably real, Stephenson 218 continues to shine, a cosmic giant, living intensely, radiating brilliantly, and preparing for its final extraordinary act.